Welcome to this video. In this video, we are going to discuss about summing and averaging amplifiers using operational amplifiers in non-inverting configuration. We have already discussed about summing, scaling and averaging amplifiers in inverting configuration. As different from the inverting configuration, here all the three inputs are given to the non-inverting terminal through resistors are same resistors. For simplicity, here we have used the same resistance value R for all the three inputs. Also, the feedback is given to the inverting terminal through resistor RF and it is grounded through resistance R1. By using the superposition principle, the voltage at the non-inverting terminal V1 can be written as by using the superposition principle, we can write the voltage at the non-inverting terminal V1 as V1 equal to R by 2 divided by R plus R by 2 into VA plus R by 2 divided by R plus R by 2 into VB plus R by 2 divided by R plus R by 2 into VC. Here we have used the superposition principle. In superposition principle, the voltage at the at this node due to VA will be influenced by the parallel network. This parallel resistance network and a series resistance R. Due to this parallel network, we will get a resistance R by 2 and this series resistance R. This parallel, these two resistors, ഈ രണ്ട് VA കൊണ്ടുള്ള contribution ആണ് calculate ചെയ്യാൻ പോകുന്നതെങ്കിൽ ഇതിന് രണ്ട് resistors are parallel this R and this R are parallel. Its net value is effective resistance is 1 by R effective equal to 1 by R plus 1 by R. So the effective resistance will be R by 2. So two resistors R and R by 2 are in series. So its effect due to VA will be given by R by 2 divided by R plus R by 2 into VA. Similarly for VB and VC. By simplifying this equation, we obtain V1 equal to VA divided by 3 plus VB divided by 3 plus VC divided by 3, or it is equal to 1 by 3 into VA plus VB plus VC. Now from the previous videos we have learned that for the non-inverting configuration, the gain of the amplifier will be AV equal to 1 plus RF by R1. So the output voltage VO will be equal to 1 plus RF by R1 into V1. That is the voltage at the non-inverting terminal. So it is equal to 1 plus RF by R1 into VA plus VB plus VC all divided by 3. So we have obtained for the non-inverting configuration the output voltage VO equal to 1 plus RF by R1 into VA plus VB plus VC all divided by 3. Now we can approximate this amplifier as summing and averaging amplifier for the case if we choose RF or if we choose the gain of the circuit as 1 plus RF by R1 as unity, that is RF equal to R1 equal to 0, we obtain an averaging amplifier for which VO equal to 1 by 3 into VA plus VB plus VC. This is the case of an averaging amplifier. That is, if we choose the gain of the amplifier as unity, we obtain VO equal to 1 by 3 into VA plus VB plus VC. So it is the case of an averaging amplifier. In the next case, if we choose the gain of the amplifier circuit as 1 plus RF by R1 as now equal to number of inputs. In this case, it is equal to 3. We obtain output voltage VO as VA plus VB plus VC. That is, we obtained a summing amplifier. So in these two cases, we can see that no sign change or phase reversal occurs for the output. So no sign or phase change for the input and output, or when we sum the inputs in the non-inverting configuration, there will be no phase change. Similarly, the non-inverting input voltage V1 is the average of all inputs, whereas but in the case of inverting averaging amplifier, the output is the average of all inputs with a negative sign. This is the difference between summing and averaging amplifiers in inverting and non-inverting configuration.